In this video, we will introduce our latest work, GoIRL, a graph-oriented inverse reinforcement learning framework for multimodal trajectory prediction. Although existing data-driven methods have demonstrated impressive performance in various trajectory prediction benchmarks, they still face limitations in effectively reacting to environmental changes. This is primarily due to their heavy reliance on supervised learning paradigms which suffer from covariate shift issues, and their inadequate consideration of the drivable area attribute. To illustrate this issue, let's consider a T-junction scenario where the target agent has two potential future trajectories, going straight and turning left. During the data collection process, the ground truth trajectory is labeled as going straight. However, if a tentative barricade is set up in the intersection, the original prediction becomes unreasonable. In this case, the predictor must exclusively consider turning left. To empower the predictor with this generalizability, we present a novel graph-oriented inverse reinforcement learning framework. To the best of our knowledge, our method is the first IRL-based predictor equipped with vectorized context representations. Here is an overview of our proposed framework. We first encode the driving context, and transfer lane graph features into grid space by the feature adapter. Then, we infer the reward distribution, and obtain the policy using the maximum entropy IRL paradigm. Next, we decode Bezier curve-based trajectory proposals. Finally, we generate multimodal predictions with a refinement module. Specifically, during the decoder process, for each sampled plan, we extract features from each state, including coarse-grained lane graph features, rewards, and grid location coordinates. We then aggregate the state feature embeddings over the plan via a by-GRU encoder, and recurrently produce control points of the Bezier curve through a GRU decoder with the soft attention mechanism. This allows us to generate a continuous trajectory proposal associated with each sampled plan. The quantitative results demonstrate that our approach achieves state-of-the-art performance on both Argoverse and Newscene's motion forecasting benchmarks. Here, we present some qualitative results from the Argoverse validation set. Our approach successfully forecasts accurate and feasible multimodal future trajectories that conform to the scene layout. To highlight the advantages of our IRL-based predictor, we further compare it against the supervised model, DSP, in handling drivable area changes. Initially, both methods can generate multiple plausible predictions. When we modify the drivable attribute, and transform a previously designated free space into an undrivable area, our approach can effectively adapt to changes in the environment, and generate reasonable predictions. In contrast, the DSP model fails to respond appropriately. Lastly, we demonstrate consecutive trajectory prediction results on the Argoverse tracking dataset. Thank you for watching.